Hello, I'm Andy Clegg from Google, and I am going to do a quick presentation on some of the lessons we've learned in CBRS. We've been operating for a little over 2 years now. Um, there are way too many lessons learned to cover in a few minutes, so I've chosen the top few, in my opinion. And no doubt some of these lessons can be and are being applied to new and future sharing arrangements, such as the upcoming 6 gigahertz AFC band, the 3.1 gigahertz band, and others. So, lesson number one is that centralized dynamic spectrum sharing works. This has been a successful government and industry collaboration. We've worked together to create standards and certification tests to get the commercial framework launched. There are currently 6 fully operating commercial SaaS administrators, and 3 more are going through tests right now, pending approval of the FCC. There's more than 230,000 CBRS base stations that have been deployed and growing. More than 160 base station models have been certified by the FCC for operation in the CBRS band. There's more than 400 client device models certified for operation in the CBRS. So that would be handsets, IoT devices, those types of things. The Priority Access License or PAL tier auction raised more than $4.5 billion in revenue for the Treasury and had more than 228 winning bidders compared to a typical spectrum auction in which the number of winning bidders is small, 10 or fewer. There's more than 4,000 certified professional installers, or CPIs that we call them, who are trained and certified to install CBRS equipment in a manner that won't cause harmful interference to the incumbents. And after all of that, there have been 0 reported cases of harmful interference to any protected incumbents. So a very good track record of deployments with no reported harmful interference. Now, one of the things we've learned is that propagation models need updating. So in CBRS, and for that matter in the 6 gigahertz AFC, interference predictions are based in part on the irregular terrain model, or ITM. ITM is based on the Longley-Rice model, which was created by ITS itself in the 1960s. And it used data to create the model that dated to as old as the 1950s. Yet, we're still making modern spectrum management decisions based on a 60-year-old, 70-year-old propagation model. So in particular, the long distance propagation predictions of ITM, in particular troposcatter, is pretty important to determining the keep out areas in CBRS, like how far away interference might occur from a CBSD into an incumbent. But that troposcatter model has never been extensively validated in terms of frequency and geography and climate and things like that. And that's something that definitely needs to be done. We also need to take advantage of the latest geodata that we have to improve the data that's fed into propagation models. And in fact, as I mentioned on the last slide, no reported cases of harmful interference to incumbents has occurred in CBRS, but that could be an argument that we are overprotecting the incumbents, partly by use of overly conservative propagation models like ITM. And so one reason I say that ITM it can be considered overly conservative is, here is a Google reconstructed view of what Manhattan looks like, with a lot of tall buildings and trees and all sorts of things. But from a propagation perspective, when you use ITM in an area like Manhattan, ITM has no knowledge of the existence of these buildings or trees. It only uses terrain. So to the ITM model, Manhattan looks completely flat. And so propagation from one part of Manhattan to another in terms of predicted interference would be overly conservative. You would predict way too much interference than actually occurs, because you're not taking into account the blocking of the signal caused by the buildings and foliage and things. So it's just one reason why ITM is a very conservative propagation model. Another lesson learned is that the use of aggregate interference in interference prediction complicates things. So SASs, when they calculate interference to incumbents, have to add up the contribution of every CBSD or CBRS device base station. Has to add up the impact of all of the CBSDs in the area to the incumbent. So one reason that that complicates things is that knowledge about the different CBSDs is distributed among the SASs. I mentioned there's 6 operating SASs right now, and so a given CBSD is only under management of one of those SASs. So what happens is every night the SASs have to exchange data among each other about all of the devices under their management in order that the aggregate interference can be accurately calculated. And these data are effectively proprietary because it's all the information about your customer's device, and you don't really want to share that with your competitors, but in fact, that's what happens. The other thing that this impacts is that if a device wants to come online, it may need to wait up to 24 hours, depending on where it's located, so that the information about that proposed device can be shared among spectrum access systems, and its impact to aggregate interference can be taken into account before giving it a thumbs up or thumbs down to transmit. So that's another drawback of aggregate interference. The calculations themselves can be relatively complex. The computations can take several hours a night for each SAS. And it's because of the number of devices, the number of interference points that you're aggregating to, the fact that, for example, for a sweeping radar, which is one of the incumbents you're calculating compatibility with, you have to take into account the different beam pointing directions. It's a lot of calculations. It can take a lot of time. And aggregate interference doesn't really necessarily account for such things as duty cycles and OFDMA access and things. So for example, in 6 gigahertz, they don't use aggregate interference in the calculations there because a typical Wi-Fi access point only has a duty cycle of a few percent. And so, but in CBRS, that's not taken into account. So there are other alternate solutions that should probably be explored. For example, a simple multiple exposure allowance. You just add 5 dB to every interference calculation from an individual device, or some number that's based upon the local density of CBSD deployments in that area, updated on some regular basis, monthly or something like that. It's just one idea, but there should be better ways of doing this. Another lesson learned is that the environmental sensing capability, or ESC, should be replaced by an informing incumbent capability. So the way we detect incumbent Navy radars operating in the band is that we have a set of sensors located along the coastline. There's a few hundred such sensors. They're there pointing out to the ocean and having to detect radar activity potentially hundreds of kilometers away. In order to be sensitive enough to detect those distant radar operations, the sensors themselves have to be protected from interference caused by CBRS operating in the area so that they can hear those distant signals. So this creates what we call a whisper zone around the sensors, in which the deployment of CBSDs is either prohibited entirely, or each CBSD has restrictions on how much power it can transmit and where it can point. And given that we have a few hundred sensors around the coast, the total population impacted by these whisper zones is quite large. In fact, it numbers in the millions of potential CBRS customers. So it's not a small impact. We believe that a better approach is to move towards an informing incumbent capability where the DoD tells us where and when they're operating, and we can protect them based upon the information they push to us. And it doesn't have to be in advance. It can be, with minutes or even seconds notice, because that's all we get right now. We get about 60 seconds notice through our ESC networks at most. This has several advantages. One is the DoD controls the information flow to us. We're no longer sensing their actual operations. Instead, they're telling us what they want us to know. It also avoids false alarms from ESC sensors that can sometimes trigger on things like motors or switches or ignition noise or whatever, because a lot of those impulses look like potential radar signatures. And then most importantly, whisper zones are no longer a factor. If you don't have sensors deployed, you no longer have any whisper zones, and those millions of people are no longer impacted by not having not being able to deploy CBRS. This is an example of a whisper zone impact. This is Southern California, basically from Laguna Beach at the lower right up through Santa Monica, up towards the upper left. And the red area are areas where you either cannot deploy a CBSD or you're constrained with regard to the total amount of power. And this is not a theoretical impact. This is based upon actual deployments of real ESC sensors in that area. And CBRS customers in these red areas are, in fact, impacted. The red areas cover over 266,000 people, 120,000 households. And we have similar areas all up and down all of the coast, impacting, from the Pacific Northwest through California, around to the Gulf Coast. Florida is very heavily impacted because it's so flat. It goes all the way up the East Coast. Manhattan is heavily impacted by whisper zones. And so, in the end, the total population under these red areas is in the millions. And then finally, in the lessons learned that I have time to address is that coexistence is important. Within the CBRS service itself, if you consider that up before CBRS, virtually every LTE deployment was in an exclusive use band where there was one licensee and they operated their own network of base stations, and they could synchronize the base stations, configure them the way they need to in order to manage coexistence among all of the different base stations. In CBRS, particularly in the lower tier, the GAA tier that doesn't require a priority access license, multiple operators share the band. And each of those operators has their own use cases, customers, and other requirements that dictate their deployment configuration. And their configuration may or may not be compatible with the base stations that are operated on the same or adjacent frequencies nearby. And so we have to create this concept of what is fair spectrum use. And industry worked on this for quite a while to create a standard or a recommendation on how we treat coexistence among the GAA tier. And we've spent a lot of effort trying to come up with it, but we've not come up with any universal definition of fair spectrum use. And so there's still, some impacts of GAAs trying to operate in the area of one another and suffering from harmful interference and having difficulty working it out in some cases. Most cases the operators work it out together, but there are a few cases that have not gone so well. And we believe that as more spectrum becomes targeted for shared use, that better, or in fact any definition of rights and responsibilities among the shared tier users is highly desirable. So a summary of this, quick lesson on lessons learned is that CBRS is commercially successful, and it's the first successful shared spectrum framework in the US or worldwide. The success is due in large part because of the successful collaboration between government and industry. However, as with any new product or service, there is room for improvement. And we believe that by taking an honest look at lessons learned, like the 5 I showed here, that CBRS and future shared spectrum frameworks can be refined and optimized to better serve incumbents and new entrants. So thank you very much. I hope this was a useful, a very brief insight into lessons learned in CBRS.